let's just recall a little bit about what we were doing last time. So what we're trying to do is determine the center of the quantum group. So we had the following kind of setup here, where we had this projection map from u lower 0 to u upper 0. So this is with the grading, and this is the commutative subalgebra generated by the k mu's. And then we had this kind of this shifting or twisting algebra isomorphism uniquely given by scaling the k mu's appropriately by this factor q to the minus rho mu. And then we could compose these two maps, and then we get the Harish-Chandra homomorphism. And then so in the classical case, we had the symmetric algebra of the Cartan, and so in our quantum case, this U naught EV will play a similar role. And so our main theorem from last time was that the restriction of the Harish-Chandra homomorphism to the center is an isomorphism onto its image, which is the W invariance of this U naught EV that I just described. Okay, so that's the theorem we're trying to prove. And so what we did last time was we proved that this map is injective, and that psi of z of u indeed actually lies in this. So what we've been concerned with then is surjectivity. So where we finished last time was we showed the following theorem, which is there exists a unique bialgebra pairing on u less than or equals 0 cross u greater than or equals 0, such that for all alpha and beta simple roots, we had the following properties. And more importantly, recall what a bialgebra pairing is. It's that if you can, it's basically a homomorphism in each component, in the sense that, so let me be more explicit in blue here. One second. So the map X maps to, and Y maps to, which are maps from u less than or equals 0 to u greater than or equals 0 dual, and u greater than or equals 0 to less than or equals 0 dual, are algebra homomorphisms. So let me say that. Where the algebra structure is on the dual space is the canonical one that arises. Okay, and then we finally had this nice lemma here, which was that you could restrict to that if the degree doesn't match on the left hand side and the right hand side, then the pairing is 0. Okay, so that's kind of where we finished with. So before we do something totally new, let's do an example. Okay, so example. Okay, so if alpha is in a simple root, then f alpha to the n, e alpha to the n is equal to -1 to the n q alpha n times n minus 1, 2 over recall that Q alpha is equal to Q to the alpha alpha over 2. Okay, so the proof for this is we're going to do it inductively. So for the case n equals 0, 1 recovers, you just get 1 bracket 1, and you'll equal 1. So not much to check there. And for n equals 1, again, this is clear because of the this, by the way, when we constructed it, we deduced that it had the property that f alpha e alpha is equal to minus q alpha inverse. Okay. So for n greater than 1, we can proceed inductively. Okay, so we want to use the following property. So we can, since we have this by algebra property, it's a homomorphism. We can write it as the following. And such, and I'll label this as a star. Okay, so let's write down what alpha to the n is. This is, of course, just by an inductive computation that we may have done in an earlier lecture. This is given by q alpha. Okay, so now we can apply this lemma 9 here, and that can. And what we notice is that if you want to match, the degree of this has to match the degree of this, and the degree of this should match the degree of this. So by inspection, you can just see that only the I equals 1 term will contribute anything. So so we can just write it as f alpha to the n, e alpha to the n is equal to f alpha to n minus 1 tensor f alpha, and then q alpha to the n minus 1 alpha to n minus 1 k alpha tensor e alpha. Okay, and then from here, it's just a matter of splitting this up. So this becomes q alpha to the n minus 1 alpha times alpha n minus 1 . Okay, now we can ignore this k alpha here because if you have a k in this component, it's just going to give you a factor of q, but the k in this component is q to it's 0 degrees, so it's not going to contribute anything. So this thing ends up becoming q alpha to n minus 1, and then it's from here you just apply the inductive hypothesis. Okay. So I hope that example is clear. Okay.
Maybe we should pause for questions, and if no questions, I will make a comment. So the comment is like this. We put various assumptions on Q, but our crucial assumption is that Q is not a root of unity. And here is one place where we actually see what goes wrong if Q is a root of unity, because if you look carefully at the quantum factorial, at a root of unity, quantum factorial can vanish. So at a root of unity, this pairing which is perfectly well defined, is not going to be non-degenerate. We can also see that somehow if we treat f alpha to the n divided by n alpha factorial as a separate entity, then the pairing is still has chance of being non-degenerate. And this is going to play some role later in the seminar. So this was a comment.
Any other questions or comments? Okay, so in that case, let's proceed. So Yvonne mentioned non-degeneracy, and so that's the next thing we're going to talk about. So we have the following proposition. The restriction of our pairing to u minus mu minus mu plus for any mu in the root lattice is non-degenerate. Okay. So because the dimensions of these two things match, so the dimension of u minus mu minus is equal to dim u mu plus, and you can see that by, you can recall this involution on u, where omega of E alpha is equal to F alpha, omega of F alpha equals E alpha, and omega of K alpha is K alpha inverse. One of these gets sense to the other, and so they have the same dimension. It suffices to check, or it suffices to show that if y element of u minus mu, so let's fix a mu. So y in u minus mu is such that for all x in u plus mu, then y paired with x gives 0. We want to show that y equals 0. Okay, so the way we're going to do this is we induct the partial ordering on the root lattice. So I mean, right off the bat, we see that if mu is equal to 0, then it's true, as u minus 0 equals u plus 0 is equal to your ground field, and 1 comma 1 is equal to 1. Okay, so this handles the base case. And so now, in inductive step, suppose that the restriction of u, or let me say it this way, restricted to nu u minus nu minus cross u nu plus is non-degenerate for all nu less than mu in the partial order given by the roots, simple roots. So what we want to do is we want to kind of break up what we have in u minus mu cross u mu into lower pieces so we can apply the inductive hypothesis. So suppose y minus mu is such that y comma x equals 0 for all x in u plus right, so we'll assume this on y, then any element in u mu plus is a linear combination of elements of the form either x e alpha or e alpha x. So I should be careful with my notation. So here x is an element of u plus mu minus alpha. So I'll change it up here. It's a t or something. Okay, so by the assumption, then that means that what we have is, so this implies that y.
I'm not quite sure about any element. Well, certainly, well, and we don't need this. Certainly, it's it's enough to consider elements of this form.
Okay.
Maybe it's, so if we know that the pairing is, if we can get, we already know that pairing is 0 with this element. If we can arrive at contradiction, this will be sufficient.
Mm-hmm. Okay, so we have the following statement.
And then, of course, at the sorry, Arun, at the end of the day, it will happen that such elements span u plus mu.
Okay, so since e alpha raises by the degree by alpha, this x e alpha will be in u plus mu, and as will e alpha x, and in any case, y will annihilate it in the parent. Okay, so in order to apply the inductive step, we need to introduce some new elements. So keep this in the back of the mind, and then we're going to kind of take a small aside here, and we're going to introduce two different elements associated to y. So so for y in u minus mu minus mu in the root lattice, define r alpha of y and r alpha prime of y as follows. So alpha is a simple root. Okay, so let's first recall, recall that delta of f beta is equal to f beta. So this is the co-multiplication, k beta inverse plus 1 tensor f beta, where beta is a simple root, and delta of k theta is equal to k theta tensor k theta, where theta is in the root lattice. So since u less than or equal to 0 is generated by these, you can show pretty directly that the delta of y, so y is in u minus mu, is in the following subspace. So you take all nu less than equal to mu, and then you consider the following subspaces. Okay, so what this means is that I can express delta y as follows. So therefore, so this is how we're going to define our elements R alpha and R prime alpha of Y. So they're going to be 1 degree lower or higher because it's negative. So delta of Y is equal to, so let me just write it first. So you can, I'm going to write delta Y in 2 different ways, but it's the same expression. Okay, so all I'm doing here is that we have this expression here for delta of Y. I can either, so nu it'll be equal to 0, or it'll be equal to some simple a simple root, and then you'll move up the kind of the lattice, and then eventually you'll come back to mu. And so nu can equal mu, or it can be mu minus a simple root. So here what I'm doing is I'm just expanding it out as nu equals 0, and then nu equals alpha, and then the remaining terms, and then this is nu equals mu, and then I'm doing it in the other direction here, just using this decomposition. So in particular, let me give myself some more space here. This term here is an element of u minus mu tensor u0 minus, and this element here is an element of u minus mu minus alpha, so it's 1 higher tensor u minus alpha minus. And then similarly, this is an element of u0 minus tensor u minus mu minus, and then that is an element of u minus alpha minus tensor minus mu minus alpha minus.
And we want to be a bit careful when you write at the very bottom of the page.
Can that not be seen?
For me, it's not fully visible.
Okay, I'll just move it. Okay, is that better?
Yep.
Okay. Okay, so let me just give you an example. So an example of this. So R alpha of 1 is equal to R alpha prime of 1 is equal to 0. And R alpha of F beta, where beta is another simple root, is equal to, also equal to R prime of F beta is equal to delta alpha beta. So you're just looking at this term here. Where is it? In this case here, or here, depending on which one. Okay.
So what essentially going on is that we just want to give names to some terms in the expression of delta of y.
Right. Okay. So so we've defined these elements, and they satisfy this nice like Leibniz style property with a q out in front, which is this property, which is a direct computation just by expanding. So let me write it, that if you have a if y is an element of u minus mu, and y prime is an element of u minus mu prime, then r alpha of y prime is equal to q to the alpha mu, and then y r alpha prime y plus r alpha y prime. And similarly, r alpha prime of y prime is equal to y r prime alpha y prime plus q to the r alpha prime of y prime. And the way to show this is you just compare, you can either expand it out as this, or you can write delta of y prime as delta of y times delta y prime, and then expand it out that way, and then compare the two terms, and you get this formula / property. Okay, and so the reason I introduced these elements is in order to prove a lemma, which we will use for proving our non-degeneracy here. Okay, so we have the following lemma. So for all mu greater than or equal to 0, y in minus mu minus, and x in u mu plus. So this is what will let us apply the inductive hypothesis. We can write y comma e alpha of x is equal to f alpha e alpha paired with e alpha times r alpha of y paired with x. That's one. And then the other one is y comma x e alpha is equal to f alpha e alpha paired with r alpha prime y of x. So this is just a matter of expanding out and using the property that delta of y to prove. It's left as an exercise, but it's just a matter of using this delta of y e alpha tensor x is equal to the first one, and so on. Okay, so what we
just write what it equals to, maybe
yeah,
just
sure.
use an arrow.
Yeah, sure. So this equals okay. Okay, so what we now know is that, coming back to our thing, is so the last statement I wrote was that y e alpha x equals 0 equals y x e alpha. So, but r alpha and y, r alpha of y and r alpha prime of y are an element of u minus mu minus alpha. And so there we can apply the inductive hypothesis here by this lemma. And since the pairing between f alpha and e alpha is non-zero, this forces that the r alpha of y with x is 0. And since x is arbitrary here, this forces that r alpha of y equals 0, and similarly in the
My
other
remark
side.
about the bottom of the page still applies.
Oh, okay. I think that should fix it. Okay. Okay, so we show that this r alpha y is equal to 0 and r alpha prime of y equals 0. But our ultimate goal is to actually show that y equals 0. And so we need the following lemma here. So for all alpha and pi, y and u minus mu minus mu, again as above, then we have the following relation. The commutator of e alpha and y is given by q alpha minus q alpha inverse k alpha minus let me go to the next line. And the proof, again, is left as an exercise. But it's easy because we already know that this is true for y equals 1 and y equals f beta. So you can check, and then you can just use this Leibniz style property here and show that it's true. If it's true for y and y prime, it's true for their product. And then that proves the lemma. But how it's applicable to us is that we just deduced that R alpha and R alpha prime of y are both 0. So this implies that E alpha and y commute. And then, I mean, from here, we're almost done. So we have our last lemma, which is if y element of u minus mu minus commutes with all E alpha, and y equals 0. And our proof is as follows. So if you had such an element, if such an let me say it this way. So we claim that such an element acts as 0 on every finite dimensional representation. And then from a couple of lectures ago, we know that this implies that y equals 0. So indeed, to show this claim, you can just consider any irreducible module M and consider a lowest weight vector. So to the E alphas, so the U plus action on V generates M. And because y is in the negative piece, it's in U minus U minus mu, y annihilates a V. And since it commutes, then you can just move the y past all the e's, and this tells you that y actually annihilates the entire module. So y annihilates M. Okay, and that, applying the lemma, we can finish the proof of the proposition, which is that because y commutes with all E alphas, y is equal to 0. And that proves the proposition. Okay, any questions at this point? Okay, so we've constructed this this pairing on U minus mu cross or U less than or equal to 0 cross U greater than or equal to 0, and we've showed that its restriction to kind of these opposing spaces is non-degenerate. But our ultimate goal is to actually construct an invariant form on U itself. So that's what we're going to do now.
Maybe may I make a comment?
Yeah, sure.
So there is you can imagine a somewhat different proof, which, so pairing just corresponds to a homomorphism from the algebra U bigger or equals than 0 to U less or equals than 0 dual. And so you can imagine that Well, actually, and okay, so this homomorphism sends generators to generators. So if you, or at least what you want to be generators. So if you define the things appropriately, you should be able to prove that the pairing is not degenerate, roughly because this homomorphism is surjective. But this requires some work and some language. That was a comment.
Okay. So our goal is to construct this invariant pairing. And then what this invariant pairing does eventually is that it gives us an embedding of U into U dual. And then we can find invariants in U dual that actually lie in the image of this embedding of U in U dual. And so their pre-images in U will be invariants in U. And those, the U invariants under the adjoint representation are precisely central elements. And so we have some central elements to work with. And then once we have those central elements, we can show rather directly that their images under the Harish-Chandra homomorphism actually can be used to produce a spanning set of U not F W invariants. So with that being said, let's define what an invariant pairing is to start with. So so let M be a U module, and this form on M cross M a bilinear form on M. Okay, this pairing is invariant if the induced map M tensor M to K is a homomorphism of U modules, where we view K as a trivial U mod. So by definition, this means that for all U and U and M prime M, UM paired with M prime is the same as M paired with S of U M prime. So of course, this is a more general definition. We don't have to just look at U. You can look at a Hopf algebra, but for us, U suffices. Okay, so now that we constructed this bilinear form on U less than or equals 0 and U greater than or equals 0, we can use that to construct a form on U itself. So we may potentially have to enlarge in the field. So there is a well-defined K bilinear map, or one should say, well, yeah, okay. There's a well-defined K bilinear map, which I'll denote with the bracket notation from U cross U to K adjoin a square root of Q if we don't have it. And the defining property here is, so I'm going to write it like this. Is equal to Q to the 2 row nu. So this is where we need our Q to the half. So x is an element of the u minus, u mu plus, y is an element of u minus nu minus, x prime is an element of u mu prime plus, and y prime is an element of u minus nu prime minus, where lambda prime are an element of z in the root lattice, and so let me make sure that everyone can see this. And mu prime, nu, and nu prime are a positive sum of positive roots. Okay, so the proof of this existence is as follows. Proof. Okay, so the multiplication map u minus tensor u0 tensor u plus induces an isomorphism of vector space, or is an isomorphism of vector spaces. And you can restrict it to the following spaces, whose restriction u minus nu minus times k nu tensor u naught tensor u mu plus to u minus nu k nu u naught u mu plus. Now, since k nu is a unit in u0, this is the same thing as u minus nu minus u naught u mu plus. So what you can do is you get this decomposition of the left-hand side in the multiplication map as follows. So therefore, we can write summing over mu nu and so then we can extend as described. Okay, so you might be wondering why there's this sort of k nu artifact here. It makes the computations nicer. At least that's the only reason I saw.
Well,
it's also
it's not just the computation nicer, it's formulas are nicer, because otherwise you will need to write formulas like lambda minus lambda minus nu paired with lambda prime minus nu prime, or something like that. Because the formula looks a little bit better.
Okay, thank you. And also, what's nice about this decomposition is it lets us use the fact that so here what we're doing is we're kind of pairing this mu. So this isn't u mu, and this isn't u minus nu prime, and a similar statement for this. So the form becomes greatly simplified if you kind of restrict to the right cases, because we know that the form on u less than or equals 0 cross u greater than or equals 0, if the degrees don't match, then it's 0. So we have the following statement. So property. U mu plus 0 unless mu equals nu. I'm going to denote this relation here as a blue circle with a dot in it. The pairing on u minus nu minus u0 u mu plus u minus prime equals 0 unless, so the insides match and the outsides match. So mu is equal to nu prime and mu prime is equal to nu. Okay, so we've constructed this invariant form. Let's talk about some properties of it. Or, well, we haven't quite shown that it's invariant, but we've constructed this form. Let's look at some properties. Okay, so so let's recall the adjoint representation. Of a Hopf algebra. So for u in U, we define the linear map add u from U to U by if delta of U, the co-multiplication in this Sweedler notation is AI tensor AI prime, then add U on some V in U is equal to AI V S, the antipode applied to AI prime. So, okay, and then now U is a U module under the adjoint representation. So we can consider what it means for this form to be invariant. And so theorem 16. The form is invariant, i.e. for all U and W prime in U, add U applied to W paired with W prime is equal to W paired with add S of U applied to W prime. Okay. So the proof of this, I mean, it's clear that we can just we can check on the generators here. So it suffices to check on the generators F alpha. Well, let me
so this is a use, right?
Sorry?
This generators will be U. Will be
right,
U.
right, correct. We suffices to check. So right. Suffices to check star on W prime arbitrary and U a generator. Okay, and so the generators, of course, we can are F alpha, K theta, or E alpha. Alpha simple root, and theta in the root lengths. Okay, and I'll actually, and because of this this circle property here, we can actually further restrict. Sorry, not quite. And we can, let me rewrite this. So not arbitrary W and W prime, but so U a generator. So let me say it like this. And W prime of the form W is equal to Y K nu K lambda X, and W prime is equal to Y prime K nu prime K lambda prime X prime, where y and y prime are an element of u minus mu minus x, excuse me, sorry. So lambda and lambda prime are, let's see, phi, nu, mu, nu prime, and mu prime are elements of z greater than or equal to 0 pi. And then x is an element of u mu plus, x prime an element of u mu prime plus, just as above. So y element of u minus nu prime minus and y prime. Okay. So it looks like we're right at the break time, and I would prefer to pause here if that's okay, and then consider after.
Yeah, sure. Let's resume at 5:03. And meanwhile, do people have questions? Or comments?
Okay, so it suffices to check this relation on the generators, and so let's and these graded components here, and so in the case u equals k theta, it's a consequence of the orthogonality relation. The form will be degree 0, and it's pretty immediate there. So what we'll do is we'll check in the case of, or we'll sketch the case u equals E alpha. Okay, so let's recall what the adjoint representation of E alpha is. It is add E alpha on T for all T and U is equal to E alpha T minus K alpha T, K alpha inverse E alpha. So what this implies is that add E alpha of W, as we've written it, is going to equal E alpha y k nu k lambda x minus k alpha y k nu k lambda x k alpha inverse E alpha. Okay, so now we're going to add in a term into this equation and also commute. So let me just write it. So we're going to add in a term E alpha y k nu k lambda x minus y e alpha k nu k lambda x. So we added this term in. We're going to, or we subtracted this term. We need to add it back in. Y e alpha k nu k lambda x, and then we're going to commute. We're going to commute one of these. We're going to commute this k alpha. So in the second line here, and so this becomes plus, or excuse me, minus q to the mu minus nu alpha y k nu k lambda x e alpha. Okay, and so if you look closely, the reason I introduced this term here is because it becomes e alpha y minus y e alpha times this k nu k lambda x. And we have a formula for that commutator. So if you apply that formula, what this becomes is this large expression, q alpha minus q alpha inverse times k alpha r alpha of y minus r alpha prime of y, k alpha inverse k nu k lambda x. So that's the first line here. And then we want to move this k alpha, this e alpha, this e alpha here, and so that it's of the same form here. And so what you end up getting is a factor that becomes k nu k lambda times q to the minus lambda minus nu alpha e alpha x minus q to the mu minus nu comma alpha x e alpha. And so that's those last two lines. Okay, so if you look at this closely, right, this, so this is an element of u minus nu minus alpha tensor, or not tensor, but u0 tensor. Oh, excuse me, I have one more step here. Okay, so then you can rewrite this as follows, because we want to write it in an appropriate form. So this becomes q to the, so when you commute the k alpha past the r alpha inverse, so this ends up becoming q to the minus q to the minus nu minus alpha r alpha of y k lambda k alpha minus r alpha prime of y k alpha inverse k alpha inverse plus lambda times k nu x. So that's the first term, and then the second term stays the same. So k nu k lambda q to the minus lambda plus nu alpha e alpha x minus q to the mu minus nu alpha x e alpha. Okay.
Actually, what's going on is that we just put our elements in the form where it's convenient to compute the pairing.
Exactly. And so if you look closely, this is in u minus nu minus alpha, u naught, u mu plus, and that is an element of u minus nu minus u0 u mu plus alpha plus. Okay, so now we have an expression for
Arun, I have a suggestion. So it should be pretty clear how to pair this element with what we need to pair it with. And then maybe we should just leave the rest as an exercise.
Right. So yeah, I just had one more statement to make here. So if you just look at, so we'll just look at add e alpha of w with w prime, and remember w prime was of the form y prime k nu prime k lambda prime x, and then our orthogonality relation forces.
Well, it's x prime in the
yes,
right
x prime.
side.
And so this implies that either nu prime equals mu, or mu prime equals nu minus alpha, or nu prime equals mu plus alpha, mu prime equals mu. Okay, so you just basically reduce it to a much simpler case, and then you can do the same thing for the other pair side, which is w paired with add S of E alpha acting on W prime. And you get the same thing, and then you can just, a direct computation, which is left as an exercise, can show that they're equal. So do the same thing for W add S of E alpha prime. Then a direct computation shows they're equal. So that shows it for E alpha. And then finally, for F alpha, you can either do the same thing with a slight modification, just it's kind of symmetric here. Or you can use the involution in the following exercise. So exercise, show that the composition of the involution with the antipode doesn't affect the form.
And this W here is actually an omega.
Right. Okay, so this shows that our form is invariant. Okay, so now what we can do is we can actually show that this is a non-degenerate pairing. So that's our next statement. So let me leave that last bit up. So for any U in U, if W in U, or let's write it this way. If for U in U, W paired with U is equal to 0 for all W in U, then U equals 0. Okay, so the proof of this, it's pretty straightforward. First, what we can do is that we can write U as we did earlier into this direct sum decomposition. U minus nu minus K nu U naught U mu plus, and since the pairing is so write U as such, since this pairing is 0 on U minus nu prime K nu prime U0 U prime plus cross U minus nu minus K nu U0 U mu plus, it suffices to, it's 0 unless, so these insights match, so mu prime is equal to nu, and mu prime is equal to, mu is equal to nu prime. You can just restrict the form to, restricting the form to U minus nu, U naught, U mu plus cross U minus mu, U0 U nu plus, and proving the analogous statement suffices. So nothing really fancy here. Okay, so what we're going to do is we're going to fix a basis U1 mu, U2 mu, up to U R sub mu of U mu plus. So here, so we fixed mu and mu, and then you fix a basis of U mu plus, and similarly, and let the following basis W1 mu, W2 mu, W R mu be a basis of U minus mu minus, such that these two bases are dual with respect to the form. So and when I say form, I mean the bilinear form that we constructed on U mu, U less than or equals 0 cross U greater than or equals 0. So Ui mu paired with Wj mu is equal to delta ij. Right, and this is possible because of our earlier proposition that the restriction of this pairing to U minus minus mu cross U mu plus is non-degenerate. Okay, so then the following is a basis. So the following set Wi nu k nu. So we did it for mu. You can also do the same thing for nu. K lambda uj mu. So 1 less than or equal to I less than or equal to R nu, and 1 less than or equal to J less than or equal to R mu. Lambda in Z phi and mu element of
well, these are fixed.
Yeah.
So
is a basis of the space minus nu U0 U mu plus. Okay, so now it's just a matter of expanding out the definition of the form. So we can just plug in these basis vectors, and so we just need a bunch of different variables to keep track of the indices here. So WH mu K lambda prime UL nu. So this is our invariant form now. Wi nu K lambda uj mu. So I'm just pairing up different basis vectors that live in this space here. And then by definition, this is just Wi nu ul nu times H mu uj mu times some other factor. So q to the 2 rho nu, and then q to the half. So again, I'm just expanding out the definition. And then because how we constructed the dual bases, this is a delta IL, delta HJ, q to the 2 rho nu, q to the half minus lambda prime. Okay, so now it's the rest of this is going to be left as an exercise, but the idea is basically each of these lambdas is defining a character, and so if you have a vector that's in the radical in the restriction, you can basically show that like the coefficients are all 0 by a similar character argument that we've done a couple of times already. So I'll leave it at that, and I'll just say that this shows that that indeed that this pairing is non-degenerate. Okay. So
does anybody have questions?
Yeah.
And meanwhile, Arun, maybe you can find a way to remove these two semi-transparent tabs from the top and bottom of your screen.
Oh, do you see? Oh, my bad. Is it gone now?
Yeah.
Ah, okay.
All right, everybody who asks a question can claim a mushroom from Professor Tengov, and what mushroom you get depends on what kind of question you ask. Okay, it may sound really hurtful to Pasha, but apparently nobody wants mushrooms.
Okay. So with that being said, I will continue. Okay, so a key fact here is the following proposition that I mentioned, which is that U in U is invariant under the adjoint representation if and only if U is central. And so the proof, I'm not going to prove this, but this is a general fact of Hopf algebras. And if you're not convinced, you can easily do it in the case of U, and left as an exercise. In the case of U.
Actually, there is a funny story about this statement. So it is indeed very easy to check. But so Kaplansky in 1975 formulated 10 conjectures about Hopf algebras, and some of them are still open. But one of them was this statement, which is actually very easy.
Thank you. So we're almost there. This is the home stretch to proving our to proving surjectivity of the Harish-Chandra homomorphism. So our goal is that we want to construct these central elements. So we have the excuse me, we want central elements whose images under the Harish-Chandra homomorphism are so that we can construct a spanning set of U not ev W invariants. And so we have the following proposition. So let lambda in the weight lattice be dominant. So that means lambda paired with a simple root is greater than or equal to 0 for all alpha simple. And such that 2 lambda is in the root lattice. Okay, then there exists unique z lambda in U such that U comma z lambda, the pairing of U and z lambda, is equal to the trace on L of lambda, this finite dimensional representation of the U action times the action of K2 row inverse for all U in U. Okay, So I just want to make a remark before we prove this. So remark, since we have this embedding U to U dual by X maps to, this is a consequence of a non-degeneracy, embedding of and a U mod hum. This is a consequence of invariance from the adjoint representation to this dual. This functional here, the pairing with Z lambda in U dual being invariant implies that the preimage Z lambda is invariant. And then by the proposition, it's central. So this kind of, we kind of we can add to the proposition furthermore, Z lambda is central. Okay, so let's prove this proposition. So we're going to need a lemma about matrix coefficients first. So let's just define the matrix coefficients and state the lemma. So if M is a finite dimensional U module, then for any linear functional in the dual space and M in the module, we can define the matrix coefficient CFM given by, so this is in U dual, given by CFM of some V in U is equal to F of VM for all V in U. Okay, and so that's a matrix coefficient, and here's a lemma about these matrix coefficients. So lemma 20. Let M be a finite dimensional U module type 1 whose weights lambda each satisfy the property that 2 lambda is in the root lattice. Then for all F in M dual, M in M, there exists unique UM in U such that CFM, the matrix coefficient of V, is actually just pairing with U for UM.
I want to do a wakefulness test for the audience. So suppose that I know that the highest weight, lambda, satisfies this property. Is it true that every other weight satisfies this property? People who consider themselves awake are very welcome to answer this question.
So the hypothesis is that it's the highest weight module?
So the highest weight of your finite dimensional module satisfies this property, that 2 lambda lies in the root lattice. Is it true that every other weight satisfies this property?
It's dangerous to ask her questions and like that, or even.
Well, it's a wakefulness test. Its sole purpose is to see if people are awake.
I know you don't want to know that everybody is sleeping.
Well, you are not sleeping. It's already good news.
I know, but I'm off, so.
Right, and all people have trouble with sleep. Yes, this I already know in my experience. And young people apparently sleep very well.
Yeah, I'm also, I can't fall asleep, unfortunately.
Yeah, okay. So the seminar takes a very interesting turn, you know, when all the people start to complain about things. Okay, anybody who doesn't have permanent sleep problems, but is currently awake?
Yeah, all of the weights differ by some combination of foods, so yes.
Okay, but Danielle, you know, you're also not that young.
Yeah, I want to be young still.
Yeah, okay, yeah, everybody does. All right, but that's of course the right answer, and maybe we can continue.
Okay. I guess maybe this assumption is that potentially M is like the direct sum of various finite dimensional modules. So each one of these highest weights has to be in Z in the root lattice. Okay, so let's prove this lemma. So proof. So uniqueness is clear. So uniqueness is clear because of non-degeneracy. Non-degeneracy. So let's just do the existence. Degeneracy. Okay. So for existence, so we have the following claim. Let mu and nu be the positive sum of positive roots, and theta in the root lattice. Then for every bilinear pairing, u minus nu cross u mu plus to k, there exists u in u minus nu minus times k nu, k theta u mu plus, such that for all x in u mu plus and y in u minus nu and lambda prime and z phi, we can say something about the following pairing with u. So y k nu k lambda prime x paired with u is phi of y comma x q to the half minus theta comma lambda prime. So let's not worry too much about the details here. The point is that you can just take u equal to the following element. And so I'm going to use the notation of this earlier proposition here, proposition 17. And so you can say u is equal to the sum phi of vj mu with ui nu q to the minus 2 rho paired with mu times vi mu k nu k theta u mu j will work. So the point is that we have an element that gives us this, and then you can just check for yourself that this element does that. Okay.
May I have a little request? So in that formula that you just pointed out, could you please write lambda prime more clearly?
Sure.
in the superscript. Thank you.
Okay, so now because F is in M dual and M is in M, we can, but by linearity, it just suffices to consider. So now we're coming back to, existence. So it suffices to consider F and M in M dual and M respectively as weight vectors of weights lambda prime and lambda in the weight lattice where lambda prime and lambda are weights. So this should be minus lambda prime of M. Okay. So then a direct calculation shows that the associated matrix coefficient, then CF of M, so this is going to eat something in U, it's in U dual, so when you decompose as such, its action on this Y on that piece is given as follows. So K mu, K eta X is equal to Q to the half eta 2 lambda plus 2 nu F of Y K mu X M, where eta is, so for all mu and nu, positive sum of positive roots, and eta and z phi, and u plus mu, and y and u minus nu. Okay, so what we're going to do here is we want to apply the claim to the following function. So we want to come up with a function as such, phi. So we're going to define the function as follows. So apply the claim to the function y comma x maps to, so phi, where y comma x maps to f of y k mu x m. And take theta to equal minus 2 lambda minus 2 nu. Okay, so the point is that this thing looks really similar to that. That's all there is. And so this thing and theta should play the same role. Okay, so what we end up getting is, so associated to this pair mu and nu, we get an element u mu nu in u minus nu, u0 u mu plus, such that w paired with u mu nu is equal to CFM of V for all V in, so excuse me, this should be W in U minus nu plus. Okay, so now what you can do is let UM be the sum of the U mu nus. So there's a slight technicality here. So this should do the trick. If the sum is finite. And so in order to show that the sum is finite, well, so let's prove this fact here. So if M is finite dimensional, then it has finitely many weights. And in particular, there are finitely many nu such that u nu plus acting on M, a weight vector as we chose at the start, is not equal to 0. So, and then furthermore, this, the action of u minus u minus mu minus u0 u, excuse me, no, this is correct. U nu plus acting on M is an element, is in the, so M has weight lambda, so this is in the lambda plus nu minus mu weight space. And so the pairing of CFM acting on the space minus mu is equal to 0 unless the weight of F, which is lambda prime, so unless lambda prime is equal to lambda plus nu minus mu. Okay, so therefore there are only finitely many pairs mu and nu such that this pairing is non-zero, and so that tells you that the sum is finite. Okay, so all this work was to just prove this lemma here, which is to show that that we can find a UM associated to a matrix coefficient if we have this assumption on the weights. Okay, but then to finish it, to finish the statement, to get our Z lambda, so since trace is the sum of matrix coefficients, we can just apply this lemma to each one of these matrix coefficients to the module M equals L of lambda to deduce there exists Z lambda such that trace L of lambda okay, and then as we remarked, Z lambda is unique and by non-degeneracy, and then it's central by our looking at invariants and their connection to the center. Okay, so are there any questions? Okay, so now we're basically done. So we can so now that we have this central element, what we can do is, so Z lambda is in the center, and if you recall, this is in U lower 0. It's a 0 degree piece, and so this thing is equal to the sum mu greater than equal to 0 in Z phi. U minus mu minus naught u mu plus, and so you can decompose Z lambda as the sum of Z lambda mu. So this is just some notation for the, so where each z lambda mu is in u minus mu, u naught, u mu plus, as above. And in particular, the projection map of z lambda is z lambda 0 in particular. Okay, so we have the final lemma, which is lemma 21. If z lambda of 0, so this lies in u upper 0, is of the form, so we can write it as such. So let me say, let z lambda be as in the proposition, previous proposition. So if z lambda equals, is written as such, actually, let me not say that. This is part of the proof. Then the Harish-Chandra homomorphism product of z lambda is equal to the following. Okay, so now let's actually prove it. So we have the proof. So we look at the projection of z lambda onto u0, and so we can write it as the direct sum of, as the sum of a linear combination of k nus, and then if we pair it with any k mu, we can write the following. So k mu paired with z lambda by just looking at degrees, this is k mu of z lambda 0, and then just by definition of the pairing, this is going to equal a nu q to the half minus nu mu. So let me rewrite that. But on the other hand, this star, so on the other hand, by the previous proposition, star is equal to the trace of L of lambda k mu k2 row inverse. Okay, but this trace is nice to compute because we have a weight space decomposition of L of lambda, and these things lie in the u0 piece, the k mu and k2 row inverse. So what we get is that this thing is equal to, just by looking at the dimension of weight spaces, it's the sum of lambda prime here in a weight dim L of lambda prime q to the mu minus 2 rho. So then if we want to put it kind of in this form so that we can see what these a nus are. So this is the same thing as the sum lambda prime in the weight lattice dim L of lambda prime q to the 2 lambda prime minus rho times q to the half 2 lambda prime paired with mu. Okay, so we get the following formula for the a nus. A nu, just by comparing this and this, we get a nu is equal to dim L of lambda minus nu over 2 q to the nu comma rho. And so that tells us what z lambda 0 looks like. sum, it's the sum nu in Z phi intersect 2 times the weight lattice dim L of lambda minus nu over 2 q to the nu rho k nu. Okay, and then we just applying minus rho to z lambda of 0 gives the result as Harish-Chandra morphism of z lambda is equal to gamma minus rho applied to pi z lambda, which is equal to gamma minus rho of z lambda equals 0.
So in other words, the purpose of gamma minus rho is cancel this q factor.
Exactly. Right, we want to eliminate this. And so we have the following, but now we have basically proven the theorem because so now we can state our main theorem again. So the Harish-Chandra morphism psi is an isomorphism between the center and U not EV wild group invariance. So we did injectivity and we did the image so we just need to check surjectivity. But now all this work we did is that we have elements. So by the lemma, we have elements of the form new element of C phi intersect to nu dim minus nu over 2 k nu in U not of BW.
Well, not only is there in U mod of, well, in that algebra, they're also in the image of the Harish-Chandra homomorphism.
Ah, yes, there, that's more important. In the image. So then a standard argument, in a standard kind of inductive style argument that you can find in Bourbaki's Lie groups and Lie algebras, chapter 8 shows that these span, so these elements span. And so that proves the theorem.
So maybe just a very quick comment. So this U0 if super W has an obvious basis of characteristic elements of the orbits. And then the base change matrix from that basis to the basis to this elements which are images of that lambda, this matrix is unit triangular with respect to, so both elements are labeled by some kind of dominant weight, and this matrix is strictly unit triangular with respect to the usual order on dominant weights. So that's the statement being proved.
Okay, so
the kind of the dominant term will come just from extremal weight spaces of L lambda, and everything else is smaller.
Okay, thank you. So that concludes our description of the center. So we have the Harishchandra homomorphism and this statement here. Any questions?
Okay, maybe we should thank Arun for the 2 talks. Okay, does anybody have any questions?